All right, why don't we go ahead and get started. Welcome back, everybody, to EE290C. So last time we were talking about clock and data recovery, and we're almost done with that. Just obviously as a reminder, Phase 3 is indeed due on Tuesday. So there's no presentation or anything associated with Phase 3. There's just a report. But make sure you're on top of that, because obviously there's not too much time left from this point. I don't need any super detailed reports or anything like that. Kind of the main purpose of having this phase in the first place is just to make sure that you're well on track to actually get everything done in Phase 4. But obviously if people have any problems or have questions or anything like that, definitely let me know. So in fact, on that note, how are things going? Any questions or anything on Phase 3? Anybody done? 50% of the way there? Just got started, okay. Anyone more than like 25% of the way there? Okay, I see. Well, okay, so I think by the end of the lecture today, actually things should be much more clear in terms of, let's say, at least the circuit details and sort of how you build a lot of the components that are typically inside of those things. But hopefully people will be well on their way, if not, let's say, complete by Tuesday, since that's, of course, when it's due. As I mentioned before, Phase 4 will be fairly obvious. It's really going to be sort of completing the entire rest of the system and obviously finalizing all the designs and the circuits and things like that. But I'll obviously talk some more about that once we've posted that. So, any questions on sort of class material from either last time or overall? Okay, so last time, as I said, we were talking in more detail about sort of clock and data recovery loops and what some of the trade-offs there are in terms of sort of the design of the loop and what the sort of estimators should look like based upon what the phase trajectories you're dealing with look like. Talk some more about some of these multi-phase issues. And then at the end, we basically started talking about what happens when you have these sort of loop-unrolled DFE types of structures and kind of the implications of that on how you build the CDR. And in particular, where we basically ended up was saying that what you typically end up having to do was do something like so-called transition filtering. So just as a reminder of what I mean by that, when we look at that loop-unrolled DFE, for example, with one tap, we said that there was multiple different types of possible transitions. So as an example, you could have transitions that were doing something like this, where of course this is the 1 minus alpha level, this is the minus 1 plus alpha, right? So we said that if you have a clock pattern, those would be the types of transitions you were getting, whereas in contrast, if instead you had something like, let's say a 1 1 0 or 0 1 1 type of pattern, then instead you might get something like the following. Right, you might actually get transitions that sort of look like this. Okay? So we said that there was a bunch of different ways that you can sort of deal with this, but one way is an example if you wanted to simplify the hardware, so that as an example, really all you need is your normal, your 2 samplers for doing the loop unrolling, something like that. And then you also have this edge sampler where you don't want to deal with adding in extra offsets and things like that. Then one way of making that loop at least work, although of course you are sacrificing sort of the update rate, would be to say, okay, you're only going to use this update when you actually detect that there's this clock transition. Okay, so in other words, again, you're filtering the data out to see that, okay, there's actually only this particular type of transition, so that indeed you will only be working on those edges when you actually take that data out and use it in the clock and data recovery loop. Okay? And by the way, I should mention that this general idea of transition filtering is not limited only to using it, for example, in these loop-unrolled DFEs. There's actually many other applications where you might do something like this. And in fact, I'll mention one of them in a second. But just as another example, if you ever were to do multi-level signaling, so for example, you have like, a PAM4 or something like that, then you'll again most likely use these transition filters. Because much like what happens in this loop-unrolled DFE, depending upon which sort of data level you're starting from and which one you're ending at, you can get very different edges, and therefore if you just blindly use all of them, you can get very sort of bad jitter in your clock and data recovery loop. Okay? Does this make sense to people, or? Okay, so let's actually just, there's one last thing that I want to mention just because it's kind of interesting in the context of clock and data recovery, which is, originally when we sort of started everything out on clock and data recovery, I said that sort of the most traditional way that people do things is basically, they have one comparator, which let's say they call the data clock, and then they have a second comparator, which they call the edge clock. So essentially what we're doing is we're 2x oversampling the data, right? So in other words, if before we had, let's say that the data was at 10 gigabits per second, then effectively we're sampling the data at 20 gigasamples per second, right? Because basically we have this comparator here running at 10 gigasamples, But guess what? We've got another comparator running also at 10 gigasamples with a shifted clock edge, right? So, as you guys will see, that obviously has some power implications. It has some implications on how you build the phase interpolators and things like that. So, conceptually at least, and we'll see that this isn't necessarily the easiest thing in the world to do, but conceptually at least, it would be really nice if instead you could just use one comparator and only running at that 10 gigabits per second. Okay, so in other words, instead of having like a 20 gigasamples per second, only having 10 gigasamples per second. Okay? Because obviously, that saves you power, it saves you overhead, it saves you die space, etc. Right? Okay, so turns out you can indeed actually do this and still figure out something about the timing information. Okay, now, in order to do that, it turns out you need to know some characteristics about sort of what the signals look like. Okay? But indeed, at least in principle, it's possible to do this. Now, it's not necessarily going to give you the same performance, but at least in principle, it's possible to do it. So this is what's known as baud rate recovery. So baud rate, baud is kind of like, I don't know why they call it baud, but, it's just another way of saying sort of, it's the same sample rate as what your symbols are, right? So if it's 2x baud, then that's like 2x oversampling. If it's baud rate, then you're just sampling it at once per symbol, okay? So in order to give you an idea of how something like this might work, and by the way, one of the most famous so-called baud rate recovery algorithms was what's called Muller-Muller, or Mueller-Muller. I'm not German, so I guess I can't pronounce this correctly. But basically, this is one of the most famous algorithms. If you're interested, you can go and definitely check that one out. It'll give you an idea of sort of what's going on. But just as an example, and just because it's easier to sort of explain, let's still assume that we're doing a loop-unrolled DFE system. Okay? Turns out you can still do this even without doing loop unroll, but it's just more obvious when you do the loop unroll DFE system. Okay? So in this previous picture that I drew here, I drew basically two types of edges. But it turns out there's actually one more type of quote-unquote edge you can get. So does anybody know what that is? And again, just as a reminder, this is 1 plus alpha, this is 1 minus alpha, this is minus 1 plus alpha, minus 1 minus alpha. So anyone know what other kind of quote-unquote transition you can get? And when I say transition, I just really mean analog voltage level changed. What other transition can you get? Not Chintan, because I know, I guess you've seen this before.
1 minus alpha to 1 plus alpha.
Yeah, exactly. You can basically do this, right? Because if you send two ones in a row, then that implies that you're going to be, if you were at this previous, if you were previously here, right, and I send another one, then now I'm going to go up to that 1 plus alpha level, right? And of course, similarly, if I was here, I could also have a transition like that, right? Now again, when I say transition, this isn't really that the value of the data changed, but notice there is an analog slope there, right? The analog voltage is not actually constant, okay? Well, so if the analog voltage is not actually constant, then that means that in principle you can actually get some timing information, right? Because as an example, if I sample that analog voltage there versus here, I'll get a different answer, right? So in fact, the way you would typically do a sort of baud rate recovery loop with something like this is what you're basically looking for is some kind of threshold that's sitting in between the 1 plus alpha level and the 1 minus alpha level, okay? By the way, what should that threshold be? Where, is there some other comparator that we might have in our system that might just happen to sit there anyways?
DLEV.
Yeah, it's the DLEV comparator, right? That's exactly where you'd put DLEV, okay? Now, to be totally fair, you might actually need another one down here, but, in principle, you don't necessarily have to have it, but, that's another sort of just, I should say this is negative DLEV, so to speak, okay? But indeed, if you were to do something like this, then you could actually use the information coming out of the DLEV comparator to also try and find the right symbol timing, okay? Now, just like we were sort of mentioning before, you'd again have to do some sort of transition filtering, right? Because you have to find things where there's consecutive repeated bits, right? So here it would have to be like a 1, 1, here it would have to be a 0, 0, and then you'd have to only sort of use the information coming out of the DLEV when you know that there's actually a valid transition happening there, right? Does this make sense to people, or? Okay, turns out again, there's actually ways you can do this even if you don't necessarily loop unroll. But the loop unrolling is kind of nice because it makes it sort of more obvious why there really is a slope on the data during that period of time. But even without loop unrolling, you may still actually have slope on that transition during the sort of at the sample position. So then in general, what you're doing is sort of looking for where is the point at which you're sort of getting the right timing based upon that slope. Okay? Does this make sense to people, or? Yeah.
So can you give an example of how you would do this without unrolling?
Okay, so unfortunately it all sort of relies on the fact that there actually will be some residual ISI in the system, right? So, and let me see if I can find a good eye diagram to draw this picture on. Where is it? Oh, do I not have any eye diagram? Oh, okay, there we go. Okay, well, so it's going to be a little bit hard to see, but if you sort of zoom into this region right here, right, you can see it's not flat, right? And in fact, you'll see there's actually transitions that are sort of doing things like that, right? And I may have other things that are kind of doing that, right? So notice there's actually slope on that data there, right? That slope is kind of due to the fact that, just as an example, if I had like a low-pass filtered kind of channel, right? If I leave it as a 1 long enough, versus if I had like, let's say a 1, and then a bunch of zeros afterwards, right? Those levels are different, right? So now you can see there's kind of a slope on this data here, right? So you could try and use that slope to actually recover some of the timing information, right? So this is in fact actually much like the loop unrolled DFE system. It's just that, if I'm not explicitly loop unrolling, the slope may be, much lower. If I have a better job of equalization, then I may be better. But that's kind of the basic idea, okay? Now this does, by the way, hint at why you're actually giving up something by doing this. And we can actually even go back to this picture right over here. Okay, so what is it that I'm giving up by doing things this way? Why is it that this may not necessarily give you the same performance as doing that 2x oversampled clock and data recovery? What do you guys think? And I'll maybe give you a hint. So just as a reminder, if I was to draw some of the other transitions, they would, as an example, look like this. Okay, that's one of them, and there's another one that, of course, looks like that. Okay, so just visually, what looks a little bit different about the red ones versus the blue ones?
Slope's kind of small.
Yeah, the slope of the red ones is larger, right, than the blue ones. Why is that important?
With the same voltage noise, it could throw your phase off more.
Yeah, exactly. Right. So remember, anytime you have something that has a slower edge rate, for the same voltage error, it's going to translate to a larger error in time, right? So that's actually exactly why with these kinds of systems, you often will have worse performance by doing something like this loop unrolled type of system than you would by having the 2x oversampling. Okay. Now, to be totally fair, that actually obviously depends upon the value of alpha, right? Because you can imagine if alpha was really big, then actually the edges you get from these other transitions might actually be better, right? But typically, let's say for a reasonable channel, that's probably not going to happen. In most cases, in particular this edge and this edge here, would actually have much better slopes on them, okay? So again, I just mentioned this because this is kind of an interesting approach, and in particular, you remember we talked about the DFE having weird timing interactions and messing up the edges? Well, if you really were to use one of these baud rate types of recovery loops, then potentially that avoids some of those issues. Because again, you're sort of really looking at the real sample position and trying to align things based upon that. Does this make sense to people, or? Okay, great. So unless there's more questions on this, this is actually most of what I had to say in terms of, let's say, the CDR design itself. So what I really want to do is now move to the next set of slides, which is lecture 14. And these are really going to be focusing on pretty much one of the most important components inside of the CDR, which is basically how you do that phase interpolation, or really how you do sort of controlling the phase of the clock. Okay? Now, as I sort of mentioned a little bit before, you could just build that sort of, timing control thing that you use inside of the CDR simply by doing something like a DLL. But it turns out that, that can, particularly if you do it sort of in an analog way, can be kind of a little bit painful. Okay? So the more common way that people use is what's known as these phase interpolators. Okay, so just to sort of give you a little bit of a, let's say, a definition or let's say more insight into what I really mean by that, all a phase interpolator is really doing is the following. Basically saying, let's say that I had two signals that basically, and let's call them even two clocks, with different phases on them. Okay? Well, if I take those two clocks with different phases, and I literally just add, the outputs together. So I have like two things that are just, one is taking one clock with one phase, the other thing's taking the other clock with the other phase, and I just add the outputs of those two things together. Then what I'm basically trying to do is get another output whose phase is in between the phase of the two inputs. Okay? So that's why it's called a phase interpolator, because I'm trying to take, sort of two endpoints and just linearly move between them. Okay? So let's sort of, that sounds really, really easy, but let's actually sort of draw this 1 second, and we'll see maybe why this is not quite as straightforward as it may at first sound. Okay? So again, conceptually, all we're really doing is we're taking one signal, and just to be clear, usually when you're doing that interpolation, that means that, you have one weight on one of the signals and a different weight on the other signal, and usually you're just moving the weights linearly between the two. So let's say this is some phi 0, this is some phi 1. I'm just going to take those two things and then add their outputs together, and then that output is going to be my output phase. Okay? So let's actually draw some clock waveforms and see what would happen if we dealt with those kinds of waveforms. Okay? Okay, so let's say that this right here is my phi 0. Okay? Let's say that this right here, and let me even draw it a little bit more exaggerated just so it'll be easier to see. Let's say that that's my phi 1. Okay, now obviously you're only drawing sort of one cycle or one half of a cycle or whatever. Okay? Okay, so now, what is my phi out going to look like? And by the way, I want you to use exactly the waveforms I drew here and exactly the block diagram I used. What's that phi out going to look like?
2 steps.
Yeah, it's 2 steps, right? So first, it's going to step up to some intermediate level, right? It's going to be flat. Then it's going to jump up again to the final level, right? And similarly in the other direction, it's going to jump down, of course, when that happens. So let's just line these guys up. Right, it's going to jump down, be flat, and then again, jump down, right? Okay, so does this look good to you guys, or doesn't look so good, right? In fact, this is really bad. So what's really bad about this? It's a long list, so just give me a few of them.
Well, you're not sure how to define that phase anymore, like the transition.
Yeah, so first of all, I don't even really know what the phase of this thing is, right? Because I don't really have a well-defined transition here, right? By the way, even if I could somehow figure out that problem, I just say, okay, arbitrarily it's somewhere in between, and I don't know exactly how I decided that, but let's just pretend I decided that. What else would be really bad about this?
Signal is no longer a clock.
Okay, I mean, you're right, it's no longer a clock, but let's say I squint my eyes and I say, okay, if I blur this out enough, it kind of looks like a clock. What's really bad about this particular clock? By the way, it all has to do with the fact that it's not really a clock and you can't really exactly define where the phase is. So, yeah.
Connected like a flip-flop to it, then it would trigger at either the first edge or the second one, or maybe somewhere in between.
Yeah, basically you might very easily cause metastability, right? Because you're sending some completely garbage analog level into the flip-flop, right? So you can certainly cause metastability. In fact, there's another thing which is related to, remember we said something about signal slopes and sensitivity to errors and things like that? What's the slope of the waveform here right when you care about it? It's 0, right? It's completely flat. So you can put, tiny little bit of noise and completely make the timing undefined, right? You have no freaking idea what the edge actually is doing. Okay, so clearly this is bad. Okay, so now, what do you have to do to fix this? How do we make this kind of look halfway okay? Say that again?
Integrate.
Okay, you said integrate. You're kind of right, but if I just purely integrate it, what am I going to get back? You're going to get something kind of looks triangular, right? And I probably don't exactly want it to be triangular, right? But you're actually going very much in the right direction. What else can you do to try and fix this? And it may not be pure integration, by the way, but it's similar. What's causing this problem in the first place?
So if you added some slope to the transitions of the original clock waveforms, such that you have some overlap.
Yeah, there we go. So what you really want to do is actually make sure that the waveforms are slopey, right? So as an example, if I did something like that, and let's say something like this, and something like this, and something like that, then indeed, okay, now what I'm going to get is something that looks, let's say, okay, there's some slope here, and then there's some other slope there, right? And then again, there's some slope there, and some other slope here. Okay, so still not perfect, but that's a heck of a lot better, right? Now I've actually got some, reasonably well-defined thing that kind of looks like a real clock waveform, right? Okay, so indeed what we're basically saying is we need to smoothen the edges out. But now there's sort of this related question, which is when I say I need to smooth them out, how do I know how smooth they have to be? Okay? And so before we exactly answer that question, I just want to make it clear why there really is a limit there and ask you guys sort of a related question to that. So let's say I do this smoothing thing and I try and make it kind of okay. Do you think you can interpolate between clock and the inverse of clock? Who thinks you can? Who thinks you can't? Okay, good. Why not? What's going to happen if you interpolate between clock and the inverse of clock? What's that going to look like?
Diminished version of either one.
Yeah, exactly. It's just going to look like a smaller version of the original clock, right? So in fact, if I made it 50% weight, it would just be a 0 value, right? Okay, so indeed, there's kind of this implication that there's a limit on what you can really interpolate between, right? So in particular, there seems to be some relationship between sort of how far apart the clocks are, and we just said that if they're 180 degrees out of phase, we're just completely hosed, and something having to do with sort of how smooth we have to make the waveform, okay? So as you can imagine, intuitively, it just sort of obviously says that, okay, well, the farther apart these things are, the more smooth the waveforms are going to have to be, right? But I'll actually derive something a little bit more, let's say, precise or a little bit more rigorous to really prove that in 1 second. Okay, so let's actually start on that now. So let's actually do a somewhat more realistic model for all of this, okay? And by the way, I should mention that this model is basically taken from Stefanos Sideropoulos' thesis. Okay, so the really sort of, it's still a fairly simplistic, but at least more realistic model, is to say, well, okay, probably the way I'm going to build this is with something that looks sort of like either two inverters or like two differential pairs or like two, like common source amplifiers, right? Where, as an example, I may have one of these current sources that's basically scaled by something like 1 minus W, and the other current source that's just W times, whatever the nominal value is. Let's say times I, okay? So this first one I'm going to turn on at phase 0. And this second one I'm going to turn on at phase 1. Okay? And then, of course, what I'm going to do with this is just, for the sake of simplicity, I'm going to assume that I'm dumping that into some RC load over here. Okay? So just to make sure it's clear, again, what I'm doing is there's going to be some sort of delay between that phi 0 and that phi 1. Okay? And let's just call that delay here delta t. Okay, so now, first of all, just sort of intuitively, what is that output? And of course, this is going to be phi out over here. And let's just focus on sort of the first edge, so the rising edges over here. What is that phi out going to look like? How would you sort of model it?
Exponentially settling.
Yeah, it's going to be some exponential settling, right? But there's actually going to be sort of two exponentials here, right? Because first, when this guy goes high, right, when this first phi 0 goes high, there's going to be some first exponential there, right? Where kind of the height of that exponential is set by how much current you have in that branch, right? Then once this second one goes high, phi 1, then you're going to have a different sort of amplitude on that exponential, right? So in other words, what we're kind of saying is that if we had just had phi 0, then we would have had one exponential settling that was related to sort of how much current we had there. And then because we added in this phi 1, we have sort of a second exponential settling that gets added into it. Okay? So in other words, if we actually write this out, so if we want to know what is the output voltage as a function of time, it's just going to be VDD minus I times R times sort of the sum of two things. Okay? So how would you sort of represent the impact of the first input, meaning the phi 0 input? And let's just say that phi 0 goes high at time t equals 0. What would be sort of the equation of the impact of that on the output?
1 minus e
1 minus W?
power minus t RC.
Okay, it's 1 minus W times 1 minus e to minus t over RC. Okay? And now, just to be sort of sure that it's clear, because in 1 second we're going to have to add something else in, that's times a step. Okay? Okay, so now, what's the impact of the second clock going high? What's the sort of equation you'd use to represent that?
Multiplied by e power minus delta t.
Okay, so is it the same thing?
Exponential.
So there is indeed a W there, but is it exactly the same thing?
T shift
T minus delta t.
There we go. Okay, so you do that times 1 minus e to the minus t minus delta t over RC, and that whole thing times u of t minus delta t. Okay, and just because there is that sort of impact of the step, that's why I had to keep track of those u of t's and u of t minus delta t's. Okay? So by the way, if you just plot out what we just wrote here, it'll indeed show you something that looks like this. Okay? And by the way, the reason for doing this is that now, if we actually look at what is delta t, and you can imagine you're always going to normalize that delta t to RC, right? Because it's really just those relative times that matter. Now what we can do is we can look at what happens as we basically change that RC relative to the delta t, right? So as an example, if the RC is very, very small, that implies that we're going to have very, very sharp edges at the output. And if the RC is large, then that's going to imply that we're smoothing things out more, right? Okay, so the good news is Stefanos already did this, so I just stole the plot from his thesis, so we don't have to repeat it. So this is a slightly complicated or interesting plot, but it actually tells you something sort of very intuitive. Okay? So what's being plotted here is this y-axis. You can kind of just consider that phase. Okay? Because remember, at the end of the day, if I have a clock, delay is the same as phase. Okay? So this is just sort of showing you what is the normalized delay of this interpolator structure that we just drew here. Okay? The x-axis here, this is just changing the weight of that interpolation. Okay, so that's just moving basically more current or less current from this side over to that other side. Okay? So obviously in the limit, kind of no matter what I do in between, if I put all of my weight on this other current source over here, then I should always have some sort of fixed delay. Right? Should always sort of have basically it's just whatever is the delay associated with that stage to begin with. Okay? Okay, now so just to make sure it's clear, as an example, let's say that my delta t is, in this particular case, 0.5 times RC. Okay? So if the delta t is 0.5 times RC, then what that's basically saying is that, and unfortunately, again, this is a slightly confusing plot, but here what's being fixed is sort of the, let's say, the RC and not the delta t. Okay, so in other words, if delta t is 0.5 RC and I put all of the weight onto that second one, then my delay would also be 0.5 RC, right? Similarly, if I put all of my weight on the second one and my RC is 0.75, or my delta t is 0.75 RC, the delay is 0.75, okay? Okay, so now, again, I know this plot is a little bit confusing. Yeah?
So what is the interpolated delay in the y-axis? Is it the
It's just the delay normalized to RC.
delay phi out to phi 1?
Basically, phi out to phi 0 to be precise. Does that make sense? And just to be really clear, you should always sort of normalize this against just like phi 0 going through the same exact structure, but with all the weight on the phi 0 side. Does that make sense? Like, in other words, don't worry about the nominal delay of the structure. Right? All we're really interested in is how does that delay change as you're moving this weight back and forth.
Okay.
Right? So the reference point is basically all of the weight on that side. Okay? Okay, so again, I know this plot is kind of, complicated, but actually the key take-home message is quite simple. So let's just take one curve as an example. So let's say that I told you that your phase interpolator sort of phase versus code looked something like that. What do you think? Are you going to be happy or unhappy? Who's happy? Who's unhappy? Okay, good. Why are you unhappy? What's bad about this? Say that again? Okay, it's certainly not linear, although remember, we're in a closed loop, so maybe the linearity doesn't matter too much. But what's actually what is definitely bad about this? And by the way, the range you're covering is obviously from here to here over a certain code sort of space. So if it was linear, oh yeah, go ahead.
Well, the resolution is kind of low in the first part and then too high in the second part.
There we go, exactly. So the problem here is that the worst case step size you're getting is crappy, right? Because if I had a perfectly linear thing, it would have just looked like that, right? So in this region right there, I have way too big of a step, so I have crappy resolution. And in that region right there, of course, I have like these really, really small steps, right? So what this is basically saying is that you really want to avoid this kind of behavior, because what you really want is something to look linear, not because necessarily you care about the linearity in and of itself, but you just want to make sure the step sizes are as small as they can be. Okay? If I'm always covering the same two endpoints, the only way to make the worst case step size as small as it can be is to make it linear. Okay? So now, out of these curves that we're showing you here then, what does that say are the curves that you think are good?
0.5, 0.7.
Yeah, it's these two down here, right? Because as I start moving up, right, as I start increasing that delta t relative to the RC, and what's happening is I'm getting more and more of this curvature over here, right? Now, by the way, as maybe should hopefully be clear, this curvature here is just associated with the fact that, we have that first exponential, right? So basically, the more we're sort of letting that first exponential settle out, the more we're getting this kind of weird nonlinearity in the delay, right? Which is, again, just very much associated with this picture that we drew over here, okay? So intuitively, this is really kind of telling you kind of what we said earlier. What we basically said was, look, we want that delta t to be very closely related to the edge rate, right? Because if we make that delta t too large compared to the edge rate, which is kind of these curves up over here, that's where we're going to get these nasty step-looking kind of behaviors, okay? So in other words, this is now we can say something much more, let's say, quantitative. When we say smooth, what we really mean is that the difference in the sort of, let's say, arrival times of those two clocks had better be basically equal to kind of the RC of that stage at the output. And that RC is very much obviously related to the edge rate, okay? Does this kind of make sense to people, or? Okay, so again, kind of the key important point is make sure that if you're building something like this, you have to be controlling the edges so that their slopes are directly tied to the difference in delay between the two things you're trying to interpolate it between in the first place. Okay? So now, how do you think you're going to do that? How are you going to make sure that, in all of the different processes and all the different corners and all the different voltages, all the different data rates you might want to run, how are you going to make sure that your phase interpolator actually has the right edge rate? And just to give you an example, it's very common for a link to need to run anywhere from 10 gigabits per second down to 1. Okay? So how are you going to ensure that this happens? Is there some magic signal somewhere that tells you something about how fast edges are supposed to be? I'll give you guys a reminder.
PLL control voltage.
Oh, what's that?
The PLL control.
Yeah, there we go. It's the PLL control voltage, right? Okay, because remember, if we're doing, let's say, our typical dual loop CDR, all right, we're going to have some PLL. That PLL is going to be essentially generating a clock frequency for us. All right, so I'm just going to draw the sort of whole loop here now. Okay, so we've got a VCO, of course, that's feeding back into the divider, and then feeds back. Okay? Well, but notice this control voltage here right? Its exact purpose is indeed to tell the VCO what is the frequency you're supposed to be at, right? And remember, inside of that VCO, there's basically just a bunch of inverters, right? Where that control voltage usually ends up controlling the power supply, okay? So in other words, if I know that I'm running at, let's say, 1 gigahertz, that control voltage is automatically going to go to whatever it needs to go to give you inverters that basically, after a certain number of delays, give you a 1 gigahertz clock, right? Okay, so indeed, what you're basically then going to do is if now I build the rest of my dual loop CDR, so again, I take my multiple clock phases out of the VCO, I feed that into some phase interpolator structure, and we'll draw that in more detail in 1 second. Right, I'm of course going to have some sort of loop filter that's again digitally controlling the phase interpolator. I have some bang-bang phase detector. Of course, I use that with the outputs. Okay? So what we're basically saying here is that indeed, if I just take that control voltage and I use it to control the phase interpolator, or in particular to control the edge rates of the phase interpolator, then now I can sort of get this nice automatic tracking. Right? Now I know that, and of course you have some minor caveats, which we'll talk about in a second. Now I know that, I've got this control voltage, and if I've done things the right way, I should also be controlling the edges inside of that phase interpolator. Okay? Now, by the way, what does that imply about how I should be building the phase interpolator? So if I'm relying on this VC right here to set an edge rate inside of the phase interpolator, how should I build that phase interpolator? What sort of type of circuits should I be using?
Ring oscillator.
Okay, basically I should be using whatever's inside of the ring oscillator, right? So if my ring oscillator has a bunch of inverters in it, then I better also be using inverters inside of that thing, right? If my ring oscillator has some other random thing in it, then I should use whatever that other random thing is inside of my phase interpolator too. Because if I don't, then I don't know that I'm actually tracking the edge rates correctly, okay? Does this make sense to people, or? Okay, so given that we said that we'll typically build this with a ring oscillator, let's look at how we would actually build an inverter-based phase interpolator. Okay, when I should say a ring oscillator using CMOS inverters. Okay? So first, let's just draw what happens if you have no programmability at all. Okay, by no programmability, I just mean we're doing a fixed phase interpolation. Okay? But I still want to do it in a way that I'm controlling the edge rates. So how would you build that with inverters? And by the way, this one looks kind of dumb. It looks almost exactly like we've done it before, but let's just see if you can get it. So how do you build a phase interpolator using inverters? And I'll already give you, 2 phases of a clock.
Just tie the outputs together.
Yeah, exactly. Basically, I have a phi 0, I have a phi 1, I feed phi 0 into one inverter, I feed phi 1 into the other inverter, I tie their outputs together, and then, of course, I just buffer that out. Okay? Now, again, the only thing to be careful of is remember, I'm trying to reuse the PLL control voltage, right? So, just to be clear, that means that the power supply of these inverters should also be set by that control voltage. Okay? Because remember, it's that control voltage that's setting the edge rates on those phase interpolators. Does this make sense to people, or? Okay. Now, by the way, once you've done the phase interpolation, after that, now you can be at whatever supply voltage you want. Right? Now you can get as clean of an edge as you'd like. Okay? Okay, so if that's the way I would build sort of a phase interpolator, period, how do you build a programmable phase interpolator? Using inverters. And it doesn't have to be exactly inverters, by the way. Obviously, we're going to have to hack them a bit. How do you do that? What do you guys think?
Break the inverter down into smaller inverters. Break the 3 inverter down into smaller inverters. Make the total weights, make the total width the same, and turning on the number of inverters based on the programmable codes.
Yeah. Okay. So then, how do you do that? So you're absolutely right. You take the two inverters, you split them into smaller pieces, and then you turn on those smaller pieces in different, either looking at clock 0 or clock 1, depending upon sort of the code, right? The digital code. Right? So now, but what's the hardware I need to do that? Like, what do I have to hack in order to get that to happen?
Put on a power switch.
Okay, you could do a power switch. More typically, that's done as some sort of a tri-state, right? Or you can also actually do it with muxes. It's conceptually all the same. But so let's just draw the tri-state version, okay? So let's say I take that phi 0, and conceptually, again, I really just had one inverter. But now what I'm going to do is I'm going to split that inverter into smaller pieces. Okay, and just as a reminder, for those of you guys who don't remember from 141, that funny-looking symbol that I drew right here, that's just transmission gate, right? So it's a PMOS in parallel with an NMOS, and with the digital control set by opposite bits, right? Okay, but then again, just as a reminder, the supply of all these guys is the control voltage. Okay, I then take, of course, the same thing, I put it on phi 1, okay? Again, I'm going to be basically programming those tri-states to decide how many of them turn on. And then, of course, I just tie those outputs together and then buffer it out, and I'm done. Okay? So as Ida was saying, given that we want to do something like, we want to keep sort of the total width fixed, right? In other words, if let's say there was a total width here of, 10 microns, then what you'd want to do is you'd program it so that whenever this was 5 microns, this would be 5. If this was 2, this would be 8. If this was 1, this would be 9, and so on and so forth, right? So you're sort of conceptually just moving width from one input to the other input, okay? By the way, there's actually many other ways you can do something similar, but this is kind of the basic idea. Okay, so does that make sense to people, or? Okay, so this is indeed actually sort of, let's say, the basic phase interpolator. Now, what I'm going to do is drive it actually sort of how you're really going to do things, or let's say what you probably will end up doing, by just bringing up a series of quote-unquote practical issues, okay? So there's going to be one practical issue which we've already sort of talked about, which is, remember, I did this whole phase interpolator thing in the first place because I wanted to make sure I could cover a full 360 degrees of range, right? I wanted to make it really easy to just completely wrap around the circle. Okay, but remember we said a second ago that it's actually kind of a pain, or in fact probably impossible, to interpolate between clock and clock bar. So that means that I need things closer together than that, right? So if they're closer together than that, how do I get 360 degrees of phase range? What do?
Provide higher resolution into the interpolator.
Okay, what exactly do you mean by that?
Instead of just clock and clock bar, you can probably break it to like clock and clock plus 45.
Okay, great. So what you do is exactly what you're saying. You don't just provide clock and clock bar into the phase interpolator. You provide multiple phases, right? And so by the way, that's exactly why when I kept drawing these diagrams, I kept drawing multiple phases coming out. Because indeed, you need multiple phases to make the phase interpolator work, okay? So what you will typically do is something like the following. And I'm just going to draw it with 4 phases now, but by no means is it limited to 4 phases. It could be any one of, a number of other ones. So this would be, let's say, 0 degrees. That would be 90. That would be 180. And that would be 270. Okay? So I'll pick one of those phases. And then I'll feed that to this, variable weight inverter thing that we just drew. I'll do the same thing on that second inverter. So again, 0 degrees, 90 degrees, 180 degrees, 270 degrees. I'll pick another clock, feed it in that second inverter, and then, of course, just tie their outputs together and buffer it out. Okay? Now, just to make sure it's clear, if this thing here is kind of indicating which quadrant you're in, you always want to make sure that this other one here is basically picking the next quadrant. Okay? So just to make sure it's sort of clear why that's the case, remember we said that we never want to be interpolating with things that are too far apart. But what we're kind of doing is trying to make sure we can walk over the entire circle. Okay? So conceptually, and I'm just going to draw this as kind of, let's say, you can kind of think of this as a phasor diagram. Right? So this would be like 0 degrees. This would be 90 degrees. Right? That's, of course, 180 degrees, 270 degrees. What I'm basically saying is that let's just start out in the first quadrant. Okay? So if the thing that I feed into that first interpolator, if I draw it in blue, let's say that I select 90 degrees, 0 degrees. If I want to be in the first quadrant, then what I should be sending to this guy over here, which I'm going to write in black, is 90 degrees, right? So that now if I do that, when I do the interpolation, I'm basically just sort of, as I change those codes, I'm just walking in between those two vectors there, right? So this would be like the first quadrant. Similarly, if I wanted it to be in the second quadrant, so it's again 0, 90, 180, 270, okay? Now, where should the blue be if I want to be in the second quadrant? And blue, remember, is the thing I feed into the top phase interpolator.
At 90.
Sorry?
At 90.
Yeah, okay. That's, by the way, it turns out there's actually two solutions, but indeed, this is one of them. You put it at 90. Okay? So if I do that, where's the other one?
180.
Exactly, it's 180. Okay, so now, and of course, if you do that, then indeed, you will interpolate basically that way. Okay, so now I'm just going to draw one arrow here. This arrow like that is when W goes up. Okay? This arrow over here is also when W goes up. So does anybody know what happens to be the other solution? And I'll just draw it over here. In terms of which one you pick to be black and which one you pick to be blue. If I still want to be in the second quadrant.
180 to 90.
Yeah, I basically just flip it, right? So in other words, I make it so that black is still here, but the blue one is over there. Okay? So now that means that, of course, the direction of that W arrow will flip, right? If W goes up, I'm actually going the other way now. Okay? Even though that's slightly annoying, it turns out that, practically speaking, oftentimes you'll prefer to do this. Okay? Anybody know why you might prefer to do this?
Then when you're at 90, W's maximum.
Okay,
when you
you're right, but
switch-
why is that important?
So when you switch, you don't have to switch W to 0.
Okay, so you're right. Now, it has to do actually with a slightly more detailed... You're absolutely right, but to understand why that's important, you have to keep in mind that the bits that are controlling this quadrant are physically different than the bits that are controlling that W, right? So imagine that when you cross that boundary, from whatever reason the bits that were changing the quadrant arrived earlier or later than the bits that were changing the W, right? So when I do this picture here, when I cross that quadrant, both of those bits have to change at the same time, right? Or rather, all of those bits have to change at the same time. That could very easily cause very big glitches, right? Whereas if I do this picture here, now basically, hey, notice the weighting that was on this sort of blue guy was already 0 anyways. So who cares, right? I'll just flip him over, and that doesn't cost me anything, right? There's no possibility for glitch because I'm not even using that output anyways, right? Then as I start continuing to go, only then do I start giving that actual weight to move it over, okay? So by the way, you'll probably see this mentioned in a lot of papers. They don't necessarily always explain it. This is indeed the reason why you do these funny sort of quadrant flips. So in general, what you'll try and do is you'll try and move only one of those arrows at a time. And you always move the arrow that has 0 weight. Okay? Make sense to people, or? Okay, great. So, that was practical issue number 1. We solved that one. Fortunately, there's a long list of further practical issues. Practical issue number 2 is actually one that's quite important and is, in some senses, very annoying. So I'll show you how to fix it, but I'll actually, as I'll explain, the fix is unfortunately a bit of a hack. Okay? So this question actually has a lot to do with sort of a concept that I think is very important, so I want to make sure people really get this. So the practical issue is really, I'm going to sort of enforce that by asking a question. So how much power is it going to take you to build a 6-bit resolution phase interpolator using this inverter-based method that we have been talking about so far? How much power is that going to take? And by the way, I don't necessarily want a number, but I want, let's say, the philosophical or let's say the underlying reasoning behind how you'd get to the number.
Well, whatever our 64 inverters switching at the full clock speed suck down?
Yeah, exactly. So what you basically said is it's going to take whatever 64 inverters is. Now, it turns out it's not quite exactly that.
It's 128, right?
Okay, well, it's slightly more complicated. Let's actually draw it and you'll see, but you've got the right thinking. Okay? So what's really going to happen is if I have a 6-bit phase interpolator, for now, let's assume that I gave you 4 clock phases. Okay? If you have a different number of clock phases, the answer will be a little bit different. But let's assume that it's a 4 clock phase thing. Okay? So remember, if I've got 4 clock phases, then that means that I have this mux in the front, right? That mux is already giving you sort of like 2 bits of resolution, right? Because it's already choosing which quadrant you're in, right? So now if I just want another 4 bits of resolution, how many sort of legs do I have in that variable width inverter that I'm drawing up here? And I'm just not going to draw them all, but how many sort of legs do you have in that upper thing right there?
16.
Yeah, you have 16, right? Because I already knocked off 2 bits of resolution. Okay? So it would go conceptually from 0, let's say, to 15. Okay? And then, of course, if this is, one of these blocks, just because I'm lazy, you'd have the same block over here, right? And then you tie those 2 outputs together. Okay? And then, by the way, indeed, if you did it exactly this way, you'd have something like, 32x minimum size inverters running at the clock rate in terms of power. Okay? Okay, so now, how does the picture change if you want to do, for example, 8 bits of resolution? Which, by the way, is not too uncommon. Maybe it's a little bit high, but not too uncommon. Now, how much power are you going to take? And let's just write this down. This is going to be something like 32 inverters at F. Okay, what's going to happen if you want 8 bits? What's that picture going to look like?
Okay.
Yeah, so how did you get there?
So 2 to the 8 minus 6. So that's how many you have.
Okay, it's actually 2 to the 8 minus 2.
Yeah, 8 minus 2.
Right, but yes. Or actually, it turns out to be minus 1, but, let's just draw it and make sure it's clear to people, right? So if I'm doing 8 bits, okay, I'm again going to have my mux. That doesn't really change, other than just sort of how much junk it's going to have to drive. But now if I look at sort of how many legs I need inside of that programmable width inverter, now actually, because I wanted that extra resolution, now I need basically 6 bits of resolution inside of that programmable width, right? So now this has to go to 63. Okay, and again, of course, you have the same block repeated below. And so that's why we got 128 inverters now at F. Okay? Okay, so now, why is this really bad? Why is this something that I told you, several times you should not be doing? Like, what's the, let's say, the quote-unquote sin that's being committed here?
Exponential increase in power.
Yeah, there's an exponential increase in power. Why is it that it's at, what's the, I said at some point, there's this combination of 2 things that each one individually you can build with no problem, but when you put them together is really bad.
Like programmability or control in the high-speed signal path.
There we go, exactly. Right, that's the problem. Our big problem here is that all of our dynamic range is right in the high-speed signal path, right? That's exactly what you want to avoid. Okay? This is exactly what you don't want to have happen. Because anytime you need high speed and high dynamic range, sorry, that costs you power. Okay? No way around it. Okay? So indeed, it turns out that this particular way of building things is not very popular. Okay? Because indeed, it couples the dynamic range you need with the high speed signal path. Okay? So it turns out that instead, what you'll actually typically do is, again, something that's going to end up being a hack, and you'll see why I say that in a second. But basically, you're going to change the interpolator structure. Okay? So instead of using inverters, what you're actually going to do is something that looks a lot more like a CML kind of logic. And I'll draw the detail in one second, but maybe just conceptually, why is it that CML logic is kind of good from this standpoint? Or rather, just generally having some current steered kind of thing. What's the beauty of doing that in terms of this problem that we just mentioned?
Total current can be kept constant.
Say that again?
Total current can be kept constant.
Okay, you're right. The total current is indeed constant, but Say that again?
Split it up and steer it? Or?
Right, you are indeed splitting it up and steering it, but like, let's say in terms of this issue right here, what is it that's really nice?
Well, you can set the current sort of in the slow domain and then just steer it quick.
Bingo. That's exactly right. So the beauty of CML logic is and let me give myself a little bit more space. I have those two current sources, right? And basically, I'm not changing them all that fast, right? So I don't have to be at really high speed when I build those current DACs. I can kind of be, okay, obviously you don't want to be sloppy, but at least I don't have to worry so much about the speed, right? So indeed, the way you will typically build these phase interpolators is indeed with some current steering kind of logic, okay? Because again, it really just decouples the high-speed signal path from the high dynamic range, okay? So this is where you do, let's say, the 1 minus W. This is where you do the W. Let's say that that's phi 0 bar, phi 1 bar, okay? And then, of course, I just tie those outputs together. And I'm going to be dumping them into some kind of load, okay? Now, in the simplest case, you'd be dumping this thing into a resistive load. But unfortunately, remember, I want to run this thing over a really wide range of data rates, right? So it turns out that what you're typically going to have to do is actually dump it into a programmable resistor, okay? There's lots of different ways to build a programmable resistor, but one of the ones that turns out to be pretty nice because it turns out to be fairly linear from the standpoint of the control voltage is this so-called Maniatis load, okay? So I'll draw it in 1 second. Maniatis is like, the last name of the guy who sort of invented this. I mentioned him previously because he was also the guy that did a lot of the preliminary self-biased PLL work. So I'll just draw what this sort of looks like, and then we'll sort of see how it goes, okay? So the load is actually quite simple. It's basically one PMOS device tied as a diode, and a second PMOS device tied with a control voltage, okay? And of course, I'll do the same thing on the other side over here. Now, it turns out this load, you don't just use it by itself, but actually what you're going to do is build another bias circuit that also uses that VC to make it so that the swing you see here is also set by that VC, okay? So in other words, this sort of load makes sure that, obviously when there's no current flowing here, it's at VDD, and when there's the full current flowing there, it goes down to VDD minus VC, okay? So the way we build that sort of, let's say, replica bias kind of thing is going to look something like this. Okay, so I just take the same resistor structure with the same control voltage. Then what I'm going to do is I'm going to basically sort of take something that's called like the half buffer replica, meaning it's just sort of like taking half of the circuit configured in a static way to kind of mimic what's the swing you're actually going to get. Okay, so I'll just draw that. And then, of course, I'm going to have my current source down over here. I'm going to control, and by the way, obviously that current source down there in this case would be an NMOS transistor, but I'm just drawing it as a current source for the sake of clarity for now. So what I'm going to do is then just take an op amp and control that voltage over there so that that swing is set by the VC. Okay? So in other words, what I've done here is I've said, well, look, when I know that this is pulled down, then that means that the input is high, right, or VDD in other words. So all I'm doing is I'm using this op amp here to ensure that when that input is indeed high, I get that control voltage of swing. Okay? Does this make sense to people, or? I see some shaking or nodding, so I'm not sure if that's a yes or a no. No. Okay. So if I just looked at this sort of circuit here, right? This op amp is just saying whatever VC is, that's what I want to put right here, right? So imagine that I made this 100 millivolts lower than the supply voltage. This op amp is going to tune this current source so that whatever that current is, when it goes through that resistance, gives you a swing of 100 millivolts down from the supply, okay? So then what I'm doing is I lower that VC relative to VDD. I'm doing sort of two things simultaneously. First, obviously, I'm reducing the resistance, right? Just because the VGS of that transistor in parallel is increasing, right? Or the magnitude of the VGS. Second, I'm also increasing the swing, okay? So that's really how I control that resistance, which also obviously controls the sort of edge rate that you're dealing with. Does that make more sense now, or? Okay, great. Okay, so now, by the way, this is indeed, at least maybe not this exact structure. You may actually flip it over, and I'll explain why that is in 1 second. But this type of structure is indeed what you'll typically use to build a phase interpolator with that edge rate control in it. So now, what's the really annoying thing about this?
If your VC goes down, your resistance decreases, but you have more voltage drop, doesn't that mean a lot of current?
That means that I'm increasing the current. But by the way, that's exactly what I need to do. Because remember that when I have lower the resistance, I'm trying to increase the frequency. So if you just think of it from like a CV squared F standpoint, that's kind of the same thing that I'm trying to do here, just in the analog domain.
It's not the same thing as your PLL anymore.
Yeah, there we go. It's really annoying, right? Because this is not the same as the PLL anymore, right? In the PLL, I really wanted those inverters, okay? Now, you could build your PLL so that it looks like this, but this tends to have sort of more headroom issues. It tends to not give you sort of as good of a phase noise for the sort of same supply voltage. There's some other, let's say, more detailed things, but indeed, you tend to want to use the inverters inside of the PLL and this inside of the phase interpolator. So that kind of sucks, right? Because now they're not the same. Well, okay, so turns out that even though this really is kind of annoying, nonetheless, it's fairly common for you to do these two different things. Basically, a ring inside of the PLL and this Maniatis CML kind of thing inside of the phase interpolator. Okay? So just to sort of draw kind of again what that would look like, let's say this is the control voltage from the PLL. I'm not going to draw the whole loop. And I used that to regulate the supply voltage of my ring oscillator. Okay, so then inside of here, again, I'm going to have some, inverters. Okay, and then, as we said before, to do the phase interpolation, I actually have to grab multiple of those phases at the output, right? So let's say I just grab these two just for the sake of example, okay? And obviously there's really muxes there that decide which ones you grab, but I'm just drawing this for the sake of simplicity now, okay? So now, unfortunately, what I have to is, take those outputs and then feed them into this Maniatis-based phase interpolator, okay? Well, and we said that in that and I'll just draw that as sort of, these two triangle things with, the controlled weight over here, okay? But remember, I really need to control the slew rate of those phase interpolators, right? So now I again need something that tells me something about, what is the actual frequency that you're using? Well, just like before, the most convenient thing to use is still that PLL control voltage. Okay? Now, the only piece of bad news is that PLL control voltage really is not looking at the same structure as the phase interpolator is. But the good news is, it's kind of similar. Okay, I have to wave my hands furiously, but it's kind of roughly similar. Okay? So what people really will typically indeed do is take that control voltage, feed it to that bias generator block, and of course to the phase interpolators themselves, and then just hope that those things are close enough that it works. Okay? Because, the good news is the edge rate doesn't have to be perfect. It just has to be sort of slow enough that things don't look nasty. Right? Okay, so just one, let's say, minor detailed thing, which is this control voltage here is really referenced to ground, right? So in other words, when the control voltage goes up, the frequency goes up, okay? So if I'm going to be using that same control voltage for sort of this bias generator kind of thing, that's why you have to flip it over, okay? So in other words, your programmable resistor will now become an NMOS programmable resistor, right? And the current source will be sort of the PMOS, okay? So when you really do it, you typically will take this and just flip it over. Okay? The other thing you will do, because as I said before, this is a hack, is you'll very commonly put something inside of here, which is some sort of programmable either divider or offset or something like that. Okay? Now again, here's where the hack really comes in. What you'll typically do is you'll just have something that says, oh, I know I'm in this version of the process, and roughly speaking, there's this divide ratio that I need to make this thing work in this version of the process. Okay? Again, this is a major hack, but the good news is, in practice, it mostly works. So, most of the time you can find a wide enough range of things that it kind of works reasonably well. Okay? Does this make sense to people, or? Okay. So, that's, practical issue number 3 is now done, although I said, we had to solve it with a hack, but that's life. So there's one last practical issue that I want to mention that turns out to actually be probably more important than well, actually, I wouldn't say more important, but equally important to a lot of the things we've talked about already. So to sort of point out what this issue is, what I want to do is actually draw what a typical code versus phase looks like for a phase interpolator, especially probably the first time around that you build one of these things. Okay? And let's just assume that, again, for the sake of simplicity, let's assume that I have, again, 4 phases that I feed to the input, that I mux between. So I have 0 degrees. Oh, oops, excuse me. I would have, let's say, 0 degrees down here, 90 degrees there, 180 degrees there, 270 degrees here, and then, of course, eventually I'll have 360 degrees. Okay? Okay, so let's see what happens if I would sort of typically do this. Okay? Well, okay, so if you actually look at what the curves typically look like, they tend to look something like this. Okay, so they kind of have some curvature over here, and then they get to that quadrant, and they jump. Okay? And then again, it has some curvy little thing, gets to the quadrant, and jumps. Okay, and then again, some curvy thing, quadrant, and jumps. Okay? And by the way, this is, again, this is a very common curve for you to see. Oh, and I guess I didn't do that too well. Let me do it. There we go. Something like this. Okay? Very common curve for you to see in terms of the phase versus code. So now, here's the fun question. What in the heck causes that? Why do you get these jumps like this?
Mux have to switch.
Ah, the mux switched. Why is that bad? Why does that cause a problem?
Well, you go back to 0 on that funny looking plot.
That's true. You do go back to 0. By the way, there is a way to make this go away. But why is it that, changing the mux code does something funny to the phase of the output? And by the way, I'll just give you a hint. Pretty common way for you to build that mux would be for something like this, with 2 stages. Okay, so there might be 0 degrees here. Let's say there's 180 degrees there, or let's actually just make it 90, doesn't matter. Let's make this is 180, and let's make that 270. Okay, and then this is your final clock at the output. And obviously there's 2 sets of control bits here. So now, why is it that changing that... By the way, obviously when you change the quadrants, that's directly associated with changing the mux codes.
To do with capacitance changing or something? Or?
Ah, okay. It could be the capacitance changes, although if you build the mux right, the capacitance itself, I should say, the cap driven by this thing may not necessarily change, although that's certainly one possible issue.
Is it because the selection signal of the second stage mux, there's a delay between the two?
Second
The
stage.
first-
I think that's more of a glitch issue.
Okay.
But there is indeed something that's kind of subtle, which is, you guys are all like homing right around where this is. It does have to do with capacitance, by the way.
Your
Delay between the paths are different than,
Okay.
than when you're interpolating, say when you're flipping between 90. So first you're initially interpolating between 0 and 90, but then you want to flip to 90 and 180. If that delay between those 2 signals changes, then that step is
Yeah, that's absolutely correct, right? If there's some mismatch in these paths, that's going to cause this jump, okay? So indeed, if there's some transistor mismatch, that would exactly cause this problem. Turns out, even without transistor mismatch, you will typically get this problem. So, and I think, Igor, you had your hand up. Any,
I mean, the mux structures are not very symmetric, right?
well, what do you mean by that? So you're right, but what do you mean?
Well, I mean, there's like transistor stacking, stuff like that.
Okay, but again, let's assume I do a good job, and I make it so that this path, at least nominally, from the standpoint of, let's say, the bare transistors by themselves, is similar to this path over here. Okay, well, nominally, let's say.
Does that do the mismatch between PMOS and NMOS? Or?
That could be there, although that's not quite it.
is it because of mirror coupling or something?
Ah, there we go. It's the feed forward. Okay? So the really annoying thing about this is that, remember, I've always got these darn Miller caps, right? And, okay, I ran out of space, so I'll do it down over here. Right, I've always got these darn Miller caps between the inputs and the outputs, right? And so what's going to happen is that if I choose a different clock phase, the impact of that Miller cap is going to be different, right? Because in one case, it's kind of pulling you forward, and in the other case, it's sort of pulling you backwards. right? So now depending upon which thing I've actually chosen, I'm effectively going to be creating a different unintentional phase interpolation at the output, right? Because as an example, imagine that I had, let's say, 90 degrees here and 180 degrees, right? And let's say I flipped it so that now instead I had, I don't know, let's say this becomes 0 degrees and this becomes 270 degrees, right? If you look out over here, phase interpolating between those two is not at all the same, right? Does that make sense to people, or? All right, so again, the real trick here is that unfortunately you always have these Miller couplings things, okay? And when you have that Miller coupling, if you start changing the inputs into the Miller coupling, if you're not really careful, you can very easily just create deterministic errors in what you're actually interpolating against, okay? So, given that that's the case, how do you think you're going to sort of, I guess it's already on there. How do you think you're going to solve it? What's sort of the easiest way to solve it? What do you do? And you know, as you saw, you can turn over the page and you'll get a very good hint. So what do you do?
Reduce the LO feed.
Okay, okay, that's one answer. You could try and reduce the LO feed through. Unfortunately, that's actually pretty tricky. I mean, it's possible, but that there's actually a more, let's say, direct way of doing it.
If you had dummy caps or something.
You're kind of going the right. You could actually do something like that. That would kind of work. But there's one that's, let's say, there's one like very simple structural fix that at least conceptually doesn't require any extra hardware.
Maybe switch the order of the phase?
Maybe, although I think that's still a little bit tricky. By the way, how many different ways are there to build a 4-to-1 mux? Is this the only way to build a 4-to-1 mux?
Do you just have all of them together?
Yeah, there we go. You build it all as one big stage, right? Because if I build it just as one big 4-to-1 mux, all at the same point, then now the coupling is always there no matter what phase I'm picking, right? So now it doesn't really matter the fact that they were all coupled because basically it's a constant coupling, okay? So by the way, this turns out to sort of at least be conceptually similar to, if you're RF people, kind of a double balanced Gilbert quad. It's not exactly the same thing because you're not really double balancing it, but it's kind of a similar idea. Okay, so the way this thing would look is something like the following. So now instead of just having basically sort of two currents that I'm going to be tuning, and again, this is all, of course, assuming that I have the 4-quadrant, the 4-phase kind of system. Now I'm actually going to have 4 currents. Okay? So as an example, I would have something like, let's say, phi 0, and then over here, this is going to be phi 0 bar. That's also phi 0. And over here, this is going to be phi 1. That's also phi 1 bar and phi 1. Okay, and then I just connect all the sort of appropriate outputs together. Right, so this is there, this is there, this is here, and this is there, this is there, this is there. I'll add the dots just to make sure it's clear. Okay, and then of course I just take those two outputs and I dump it into my resistive load. Which again, remember, the resistive load may be Maniatis or something else. Okay? So again, notice the trick here is that now all of those different phases are always coupling into the output, right? And so because of that, now, at least in principle, everything should be sort of match across the different quadrants. Now, to be totally fair, again, this isn't exactly correct, because the coupling actually changes a bit as you change those codes, okay? So if you really wanted to do it like really, really well, you can really do sort of the Gilbert quad version. Okay, so that involves, let's say, another layer of layered switches, kind of beneath this. But, don't worry about it too much. Usually, unless you're shooting for really, really high resolutions, that's probably not super critical. Does this make sense to people, or? Okay, great. So actually, that's the end of the practical issues with normal phase interpolators. Okay, so, if you do something sort of like this, or in fact, you don't necessarily have to do it all directly at the output. You can, in fact, actually do things where you just have one big mux and then feed that into the buffer stages. That also works fine. But indeed, this is sort of a fairly common way of doing things in terms of phase interpolators. Now, having said that, that's not to say that there aren't some other alternatives that in some cases may have some, let's say, practical benefits. and in particular if you're shooting for some very, very high frequencies, it may actually be sort of more convenient to do things in a slightly different way. Okay? So one of the, let's say, newer versions of things that people have been, demonstrating more recently that, again, may have some practical benefits is actually, rather than doing sort of phase interpolation with these structures that we've shown in a kind of, let's say, direct fashion or maybe an open loop fashion, is actually to use what's called injection-locked oscillators to create that phase interpolation. Okay? So to understand why this does something, we have to sort of first, of course, understand what the hell an injection-locked oscillator is in the first place. Okay? So let's just draw some ring oscillator. Okay? Let's say it looks something like this. Just, 3-stage simple ring oscillator. Okay? And let's say that, nominally speaking, if I didn't touch that thing, it would have some nominal clock frequency. And it would just oscillate at whatever that nominal clock frequency is. Okay? Well, as hopefully the name kind of implies, what injection-locked oscillator is doing is it's saying, well, you know what? Let me take actually another clock. And let me sort of inject that clock into the oscillator. Okay? Well, turns out that if that clock that I inject into the oscillator is close enough in frequency to the real oscillator itself, you can get those two frequencies to line up with each other. Okay? You can actually get it so that the frequency of the oscillator is indeed set by the frequency of that input that you give it. Okay? This has to do with some nonlinearities in the system and stuff like that. But actually, I'll give you a little bit of an intuitive view as to why that might happen. Okay? So just as an example, let's say that I take that injection signal, and just as an example, I make it a little bit faster. Okay? So let's draw that. Let's draw this clock injection. Okay? And let's say that, somehow magically I nominally got it to line up on that first edge with the main clock. But again, then I make the thing just a little bit faster than the main clock. Okay, so let's say it actually, goes high sometime like there. Okay? So, okay, during this time, because I magically lined them up, kind of nothing is really happening, right? But notice, on this edge over here, that injection clock is earlier than the main VCO clock, right? And hey, by the way, these two inverters with their outputs shorted together, that kind of looks like a phase interpolator, right? So what is this thing going to do to the main clock? Which direction is it going to move it? Early or late?
Early.
Yeah, it's going to move it earlier, right? So once this sort of injection locking thing is, let's say, locked, meaning you've sort of hit a steady state, then indeed what you'd see is that the phase of that thing would actually move in sort of earlier than you nominally would have expected it to be. Okay? Now, it won't be lined up with this, so maybe I'll draw that a little bit more carefully. But it'll actually be skewed. Okay? Turns out that the amount that it's going to be skewed by is directly related to the frequency difference between the two oscillators. Okay? And the picture that hopefully will make that sort of, give you an idea of why that's the case is imagine that I made this injection clock like really fast, right? So again, I'll just line up this first edge, but I'll make it, the next one like, much earlier, right? If I make that edge much, much earlier, that kind of implies I'm pushing that nominal clock in farther, right? Or to say it another way, like this oscillator here is always going to be chasing that injection clock somewhat, right? And because it's chasing it, how much it has to chase it, sort of tells you how far off it's going to end up in steady state. Okay? So by the way, this sort of effect is what's known as Adler's equation. Okay, that just has to do with sort of when you do an injection locking oscillator, sort of what is the phase shift you end up with as a function of the frequency offsets. By the way, maybe just as another way of seeing this is kind of like saying that, we're taking like that ramp input and feeding it into a first order feedback loop, right? So the sharper that ramp, the more delta in phase you're going to get. And it turns out that if you actually adjust the frequency either direction, meaning if you either increase the nominal frequency compared to the injection frequency, or you decrease it compared to the injection frequency, you can actually move the phase both positive and negative. Okay? Now, turns out you have to, let's say, play some games to really get this to give you a full 360 degree of range. Because once actually things are pretty far apart in terms of frequency, you get into sort of these fairly non-linear types of mechanisms. But the good news is, indeed, you can actually do that. Okay, or at least you can get about a 180 degree range. And if you can get 180 degrees, you can get the rest just by inverting the clock at your output selectively. Okay? Does this sort of make sense to people, or? Yeah.
So isn't the duty cycle set by the delay of the inverters?
The duty cycle. What do you mean the duty cycle?
To rise and fall, it's roughly about three stage delays.
Uh-huh.
But if you inject the locket to another frequency, the delay itself won't change, right? But
Yeah, okay. Oh, so maybe you're asking, just to clarify, what you could be asking is, well, hey, wait a minute, you only injected into one point. So isn't that going to cause some asymmetry,
okay.
right? You're absolutely right. If I just injected into one point, it would indeed cause asymmetry. Okay? So when you really do this, you'll tend, you might actually even want to inject it into multiple points. Okay? With different phases on those inputs. Okay? Now, alternatively, if that asymmetry is sufficiently small, or, by the way, you will typically not actually do this with a ring oscillator, but you'd actually do it with an LC oscillator. When you have it with the LC oscillator, now you only have one stage, and so that asymmetry is not that big of a deal. But, I'll draw that maybe in a little bit more detail later on. But you're absolutely right. If you do it exactly as I've drawn it here, that will cause some asymmetries. Okay, other questions on this? Or? Okay, so we'll finish up with sort of the injection locking stuff next time. So I'll see you guys all on Tuesday.